I want to show you, I want to demonstrate a concept I learned today. I'm going through data structures and algorithms. So data structures is a way to organize your data. So let's say you have a survey and then you have a bunch of data coming in. It's really hard to parse them out if you don't have them structured. Maybe you put them where it's one responder, one row, and yeah, just each row is dedicated to each responder, and then the columns might be different questions and responses. Anyways, so that's data structure. Algorithms are instruction manuals for the computer, so you're writing different strategies or techniques for the computer to achieve a certain task. So today I learned linear search algorithm. As this name suggests, you have to do this thing linearly, and searching you're finding, and algorithm's just instruction. So the question might be, hi, can you help me find a mirror cube? Here's a cluster of puzzles, and the first steps are, let's establish what a mirror cube is. A mirror cube is a single color, and in this case we'll say shiny silver color, and it's a 3x3 structure, and it's not equal. Like the pieces aren't equal, but don't focus on the diameters or the specs of it. Just look for a shiny cube that's the same color all the way around. Well, that works out because all my other cubes, each face has a different color. These have different corners and centers. This one's even like, it's a morphed cube. It's not even a squared cube. Okay, we've defined what a mirror cube is. The distinction or the unique qualities about this is that it looks like a mirror, hence the name mirror cube. Great. We've defined the thing we need to look at. We know what we need to look at. Let's say I have all this hidden and I ask you, where do you think the puzzle is? You don't even know how many puzzles I have, so you might just point, oh, in the middle. Checks the middle. Nope, the middle is a 2x2. Heck, it might be out here. It might not even be in my pile, but you don't know how big my pile is. My pile could be expanding out here. My pile could be just this much. So yeah, you could be guessing for an eternity before you actually find it. Instead, let's set up some more parameters or guardrails. We'll just choose 7 puzzles. So I'm going to pick 7 colorful puzzles. 2, 3, 4, 5, 6, 7. Good deal. These are my 7 puzzles. Ignore the other ones. Now let's line these 7 puzzles up. Here we go. Okay, there we go. Now, what these sticky notes represent are their seat numbers or their positions. So in coding, we always count from 0. So the first cube starts at 0. So this is a skewb. Skewb starts at position 0 and we go all the way up to 6. And now, again, pretend like you don't see this line of puzzles, but you know that there are 7 puzzles. So when you're randomly guessing, at least you know you shouldn't guess higher than 7. Maybe say it's a 3rd puzzle. So this is your prediction. But I'm going through each single one. Not a mirror cube, not a mirror cube. Your prediction is wrong. Not a mirror cube, not a mirror cube, not a mirror cube. Hey, we reached a mirror cube, and it happened to be at the very end. This process is called brute force because you're going one element at a time, and it's not efficient because you're exhausting all your energy just to get to it. Had you known, let's say the puzzles were visible, had you known, you might have started on this end and counted. Well, if you start at this end, you only had to go through 1 cube to find the mirror cube. So anyways, let's switch it up and say that the mirror cube is now situated here. So when you write let's use linear search algorithm, where you're going in a linear fashion, incrementing one puzzle at a time. You go 0, 1, 2. Oh, I found the cube. You only have to go through 2 puzzles to find the mirror cube. So you return the mirror cube is at position 2. And you said that you predicted that it might be the 4th cube, which is positioned at 3, because we start counting from 0. So the 4th cube would be 0, 1, 2, 3. And you thought this was a mirror cube. This was a prediction. So does my result match the reality? Or match your prediction? Your prediction was this, and the result is this. So it will return the position of 2. Does 2 equal 3? No. So then the second output would be false. So false is also a type of data structure called Boolean, which is true, false, 1, 0. So because the reality that the mirror cube is situated at position 2 does not match the dodecahedron cube positioned at 3, then it's false, but at least we know where the cube is. Let's say you were to predict, I think the mirror cube is probably the 3rd in line, and it happens to be 3rd in line, then spits out the position equals 2, and the prediction matches reality, so the argument is true. So yay, double win. Yeah, so that's how linear search algorithm works. It's really quite simple, but I want to consider other things. What if, let's say you are helping me to find the mirror cube, but we don't even have a mirror cube. But you don't know that. This is just hidden. You're going through from the beginning all the way to the end, and you say, I didn't find the mirror cube. What do? Return cube not found. What if, let's say, we do have a mirror cube, and it's in the middle, okay, like this. Then I want to propose something like, why don't we start, rather than at the edges, the beginning or the end, why don't we start from the middle and split out? Because it'll be equal distance, and have two engines looking, 2 processes or 2 loops. So one that incrementally goes backward one incrementally goes up 1. Now let's say this is the center of the 7 cubes at position 3. We start here and we go 1 cube to the left and right. This loop that's going incrementally up found the cube first, because this is not the mirror cube, but this is. Great, break the loop because we found the answer. This is much more efficient because you have imagine 2 people searching rather than 1 person. And let's say if it was at the end, then I want to have 2 loops running. 1 running from the beginning, 1 running from the end. Well, the one from the end will reach it much quicker than the one on your left, my right. So if you start here, it would be 1, 2, 3, 4, 5, 6, finally 7. But if you start from the end, it would be just 1 cube, found it, don't need to look through the rest. Now let's say we're no longer looking for a mirror cube. Rather, we're looking for 3x3s. So 3x3 is defined by 3 layers, 3 rows by 3 columns. So this is a classic cube. Here we go. So I have 1, 2, 3, 4 3x3 cube in this lineup. But we did not define find the 3x3. We just said find 3x3. Well, if I'm going to start from here, I found a single 3x3 cube in the first position at the position called 0. Okay, we found it, return that. Because look at this. This is much more different than this one. This one has like the Chinese characters. This one is just a regular, it's an electronic 3x3. So yeah, that's something. So repeating cubes. As soon as it reaches the first one, let's say it was like this, and it was going systematically from your left to right, then it's going to go this is Masherminx, by the way. It goes Masherminx, oh, 3x3, found it, done, because it's looking for a single 3x3, not a particular 3x3. If, let's say in the beginning I had asked specifically, I want a Lubix 战池, or like American people say, 三七 cube. This was my first 3x3 cube. If, let's say I was asking for this very specific brand 3x3, then it's gonna go, not it, not it. Oh, okay, we found a 3x3 and it's a specific brand you wanted, and it sits at position 2. So yeah, those are some specialty cases where they're repeating cubes. What if, let's say, we have them scattered throughout, like this? Yeah, every other would have 3x3, not a 3x3, 3x3, not a 3x3. You get the idea. So, what if it's like this, where their positions aren't side by side, they're scattered throughout. So if you don't clearly define what 3x3 cube you're looking for, it's just gonna spit out the first 3x3 cube it finds. Well, there's this Volk 3, that's the name, Volk 3 cube at position 0. Forget the other 3x3 because I already found it at the 0 spot. Or it might not know, it might spit out 2, because that is also true. It might spit out 4, that's also true, and it might spit out 6. So yeah, anyways, those are some of the cases. Oh, even more fun. Let's say I asked you to find a mirror cube, right? But I only have, in this list, I only have one mirror cube. And I say, hey, can you find a mirror cube? And the parameters are, there's only one cube in the list. So you're gonna say, I'm just gonna guess that that cube is the mirror cube. And it happens to be, yeah, it is. There's only one cube, and that one cube is a cube I'm looking for called mirror cube, positioned at 0. No other cubes, no other indexes. Let's say I ask you to give me, or help me find the mirror cube, but the array is empty. There are no cubes. Then there's nothing to sift through because there are no cubes to query through. So then the return might be false or cube not found or whatever. It might throw an error. Let's see. If it started at the beginning, if it started at the end, if there were repeats, if there were multiples in the same order. Okay, I think I went through other cases. These are different possibilities or different what ifs, but the industry term is called edge cases, so anomalies or rare cases. So for most of the time, if someone's asking you to help them find a cube out of 7 a puzzle out of 7 puzzles, you're going to guess that there must be 7 puzzles, not knowing that they might be tricky or sly with having no mirror cube to begin with, or heck, no cubes at all to look through. So anyways, yeah, I thought this might be a fun demonstration. Yeah.